Hi, this is Brian Nett at howradiologyworks.com. I'm going to talk today about how do we monitor that the systems are making good images, and particularly we want to talk about quantitative ways that we can do that. So we're going to talk about the fundamental image quality metrics that we use on radiology systems. And I won't be going modality by modality in this case because a lot of these basic definitions are the same or similar per each of the modalities. So today will be high-level overview of the different quantitative metrics that we use to assess how systems are doing. So first, we talk about contrast. So contrast is one of the most important things in a system, and the basic definition of contrast is the ability for us to see signal level of a lesion, for instance, above the background. So in a nice uniform background, for instance, you could have different contrast lesions, and these lesions also could be of different size. So, for instance, a phantom that's used in CT will have inserts of different contrast and different size, and these inserts are at 0.3%, 0.5%, and 1% contrast, and then of varying sizes, and also of varying thicknesses, where the ones in the middle are thinner than the ones on the outside. So again, just a high level, we want to take away contrast is the ability for us to see this signal level above the background. And image noise is random fluctuations which make interpretation more difficult. So here's an image without any noise, and then as we look in this direction, the noise is increasing. Different modalities have different physical behaviors that we talked about in the physical principles lecture. Mainly, we're acquiring the data differently. So the type of the noise is different between the different modalities. But they have the similarity that in general, noise makes interpretation more difficult. So for instance, if you look at the border, for instance, between the hair and the background, it's very obvious here, and it becomes difficult to appreciate where the border is between the hair and the background in the case where the noise has significantly increased. Likewise, our ability to differentiate the area of interest in a clinical image would be hindered by the presence of noise. So one feature that we talk about is low contrast detectability. In this case, this is the same contrast phantom that I showed on the first slide, but now that contrast phantom is shown in the presence of a significant amount of noise. And if you don't know where those lesions are ahead of time, it's very difficult to appreciate any of the lesions. And if you can appreciate any of the lesions, the ones you could appreciate would be just the highest contrast and largest lesions, as shown here. So in general, what we want to know about low contrast detectability in medical imaging is that object detection is proportional to the contrast in that lesion, and it's proportional to the size of that lesion. And it's inversely proportional to the amount of noise which is in the image. So in this case, it's very difficult for us to appreciate the lower contrast lesions, but you can see as the system is modified such that we have lower and lower noise, those lesions now become more and more obvious. So the clinical task, in order to design the best protocols for a given clinical task, what we need to do is we need to find the point in which those lesions can be readily identified, but we don't necessarily need to make an image which looks as pretty as this image down here. So some level of noise is acceptable as long as it doesn't interfere with the clinical task. And the clinical task, for instance, in this case, is the ability to differentiate these low contrast signals with respect to the background. So based on a given protocol, where the design of a given protocol is to image objects of a given size, the noise level, which is tolerable, can be accommodated. Next, we want to talk about accuracy and uniformity. So this is often conducted with a uniform phantom such as water or a tissue mimicking gel, for instance in the case of ultrasound. Here you can see one realization of this water phantom on a certain type of system. And in this case, we note that the pixels out here at the edge are in general a little bit higher than the pixels in the middle here. This is called cupping, because if you were to draw a profile across this region, what you would get is it would be high at the outside and then lower in the middle, high at the outside again. So the profile would look something like a cup. So this is called cupping. The inverse of this is called capping, in which case the center has higher values than the outside. So we're imaging the same uniform water phantom, and if you had values that were lower and then went higher down to lower, you can see that would look something like a cap if you were to plot a profile across, for instance, the center region. And then if you had uniform attenuation, you would get a nice flat profile if you were to plot a profile across this phantom. So accuracy and uniformity are both measured, accuracy being the absolute number and uniformity being the difference between that number in different regions. So these are what's called regions of interest. So we often look at the difference between the center and an average of the outside regions of interest in order to define the uniformity. So if there's cupping or capping, we will have a significant difference between the values in the center, the average values in the center, versus the average values at the periphery. And then accuracy is just, especially in modalities such as CT, where values are expected to be quantitative, accuracy is the difference between what we expect. We're looking at the accuracy, we can measure what we expect versus what we measure. And that can be done either just at the center or an average. Image resolution is next. So resolution we talk about, you hear a lot about on commercials for televisions, for instance, and it's all about the pixel size. How many pixels does the camera have or the monitor? But the real definition that we want to use is the ability for us to differentiate or to separate objects. And usually we talk about resolution in terms of high contrast resolution. So if these objects have enough contrast to be seen on their own, but is the system limiting our ability to differentiate? So here we have a bar pattern where we have a bright bar and then a lack of a bar and a bright bar and so on. And these are what we call line pairs per centimeter in CT. In X-ray imaging, they'll often measure them in line pairs per millimeter. But basically it's a cycle of bright, dark, bright, dark. And if we can differentiate the bright and the darks, then we say, okay, we can see at least down to this many line pairs per centimeter on this system. And as we go in this direction, the objects get closer and closer together. So you can see that once you get down here, it's very difficult to appreciate separate bright and dark patterns in this image. So this is a lower resolution example. And then as we can see more of the smaller objects, that corresponds to higher resolution. So that's why we can use such a bar pattern to do a visual examination of the spatial resolution that we can get in an image. So as I go up to these higher levels of resolution, I note that in each of these cases, we have the same number of pixels that we're showing. So we're showing the same number of pixels in this matrix as we're showing in this matrix. But this has the extreme high resolution, and then this has the lower resolution, because we're not always limited by the number of pixels that we're showing. We could be limited, for instance, in the case of CT, by the size of the focal spot and the size of the detector. So in general, we can think of starting with an ideal image, so this nice perfect bar pattern, and then imaging it on a physical system, and then we get something which is output. And a simple way to model it is we can think if we put a single point, just one little tiny point in, then what would the output of that tiny point be? So the blurring that happens, this is a plot of the blurring that one point would have on a given system. That's a simple way to do the modeling. And what we call that is we call that the point spread function. So if you input one single point, which is not spread at all, then how much would the signal energy be spread in space by the system, by the finite size of the focal spot and the finite size of the detector, for instance. That's called the point spread function. So one more terminology that we want to talk about that a lot of times will be measured as part of quality assurance is the modulation transfer function. So the modulation transfer function, we can think of if we had that bar pattern where we're again alternating. So these, we can think of these as frequencies because we're alternating between bright, dark, bright, dark. And these are the lower frequencies and these are the higher frequencies. This is that ideal input pattern. So if we drew a straight line right here down the center, we would get a plot that looked like this. So we would be going from the minimum to the maximum, and it doesn't matter. Here they're further apart, and here they're closer together, and it doesn't matter because this is like the nice ideal input. Then if we put it through an actual imaging system, we get an image that looks something like this. And now in this case, you can see that the amplitude, if we again do that same plot straight down here, we can see that the amplitude here is much greater than the amplitude down here. So as the objects get smaller, as the objects get closer together, those are higher spatial frequencies, and then it's harder to tell them apart on that output image. And so this is roughly the concept that we talk about in terms of the modulation transfer function. So what we want to do is measure the output as a function of spatial frequency, and that lets us see how the system responds and how well we can see objects which have a given spatial frequency content. So one interesting fact is that point spread function that we talked about, which is the blurring of a single point in the image. If we have that function and we make a plot of it by averaging this function, we can take the Fourier transform. That's the same Fourier transform that we talked about in the image generation portion when we talked about MRI imaging. We take that same Fourier transform and we can get a plot called the MTF. So in reality, what we often do is we have something that approximates a nice single point, and that can be done with a highly attenuating, very small wire. So if we image a highly attenuating small wire, we can make an image that if we plotted it, it would look something like this. And then the system will have software to take the Fourier transform and then be able to get out the MTF value. And so this is used in order to appreciate, for a given type of imaging, what kind of spatial resolution can we achieve. One thing I wanted to talk about that's unique to ultrasound is the resolution in different directions being significantly different. So in ultrasound, if you have a given what's called axial resolution, the axial resolution is the resolution in this direction away from the probe, and the lateral resolution is side to side with respect to the probe orientation. So again, we can think of the transducer. We're receiving those sound waves, we're receiving them back, and so the timing at which we're receiving them back, that affects the axial resolution, and that's very similar throughout the field of view. So even if you're a little bit closer or a little bit further away, the axial resolution isn't changing as dramatically as the lateral resolution is. So the lateral resolution is the resolution from side to side. So you can see if you're very close or if you're very far, it's more difficult to separate two given objects. So this is why it's really important when performing ultrasound imaging to set the beam such that the Fraunhofer region, or the region which has the best lateral resolution, is occurring in the area of clinical interest. But at a high level, what I wanted to just talk about and note is that ultrasound has lateral and axial resolution, which have different physical properties. Then lastly, talk about temporal resolution. Temporal resolution is complicated, and it's essentially the precision of the images with respect to time. In the cardiac section, in detail, in later lectures, we'll go into more details about temporal resolution. It's frequently reported as the time that's required to collect all the data of a frame, but sophisticated gating methods can also be used. The most basic method is to try and reduce cardiac or breathing motion by using an external signal in order to only acquire data in a certain region. So, for instance, when the heart's in a certain portion of the cardiac cycle, we would only acquire the data in that portion or only make an image of the data in that portion. Likewise, with respiratory motion, if we have an external signal that can tell us where we are in the respiratory cycle, we could make an image which is corresponding to just a subset of the time for the full breathing motion. So temporal resolution is something that's not very easy to quantify and is less often part of your daily or very often quality assurance procedures. So, at a high level, what we talked about is what types of metrics can we use to monitor systems to make sure that they're making good images. And we talked about the contrast, we talked about the noise, and with those two things together, we talked about the low contrast detectability. We also talked about resolution, and we talked about uniformity and accuracy of images. So this gives a good overview of the types of metrics that can be used to quantify the images rather than just asking the radiologist, do the images still look as good as they looked last week? We'd like to have some basic metrics that we can quantify and track how well the systems are doing over time. Again, this is Brian Nett from HowRadiologyWorks.com. Thank you.